Dear students, today let us we study about the radial probability distribution curves. In the last class, we have studied the Schrödinger wave equation and the radial and angular functions. So they are all the mathematical treatment to know about the probability of finding the electron, that is the orbital, and as well as the nodes. Today we take how these distribution curves are created and how to explain based on these distribution curves. Coming to the distribution curves for radial wave functions of 1s, 2s and 3s orbitals. When we plot the graph of the radial function versus distance from the nucleus in picometer, we get a line. So initially at 0 distance we have the maximum radial function and it goes on the decreasing. And for 1s orbital, so it will not cross the x-axis, therefore 1s orbital has no nodes. If I take the 2s orbital, it crosses the x-axis and goes to the minus sign and then it touches the x-axis. This shows that there is a node. That means the probability of finding the electron is 0. If I take the 3s orbital, so it goes below the x-axis and then it once again crosses the x-axis and goes above the x-axis. As a result, we find the two nodes. So for 1s orbital, we don't have any nodes. 2s orbital has one node. 3s orbital has two nodes and so on. In general, ns orbital has n-1 nodes. A node is a region around the nucleus in which the probability of finding the electron is least. If I take the distribution curves for 2p and 3p orbitals, there also we plot the graph of radial function versus distance from the nucleus, and there for 2p orbital we get the graph as shown in the figure. For 3p orbital, once again it crosses the x-axis. Therefore, 3p orbital is having one node, 2p orbital is not having any node. Similarly, if I take the 4p orbital, it is having two nodes. In general, p orbitals have n-2 nodes. Similarly, the 3d orbital has no node, 4d orbital has one node, 5d orbital has two nodes and so on. In general, d orbitals have n-3 nodes. Another way of expressing the number of nodes in each orbital is also given as n-l-1. For s orbital, L is equal to 0. For 1s orbital, the number of nodes is 1 minus 0 minus 1, that's equal to 0. 2s orbital is having one node, 3s orbital is having two nodes and so on. For p orbital, L is equal to 1. So the p starts from 2p. Therefore, 2p is having 0 node, 3p 1 node, 4p 2 nodes and so on. Similarly, d orbital L is equal to 2. It starts from 3d. Therefore, 3D is having no node, 4D is having 1, 5D is having 2 nodes, and so on. Now, radial probability distribution curves. So what's the difference between radial wave function and the radial probability distribution functions? So let us discuss these things here. Radial probability distribution curves are obtained by evaluating chi-square d tau in thin spherical shell at a different distance from the nucleus. Consider the orbital to consist of layers of thin concentric spherical shells. One such shell of thickness d tau between distance r and r plus dr from the origin is shown in the figure. The volume of such a spherical shell is 4 pi r square dr, and the probability of finding the electron in this volume would be equal to chi square into 4 pi r square dr. So this chi square into 4 pi r square dr is known as radial probability distribution. A radial probability distribution curve of 1s is obtained by plotting the graph of 4 pi r square dr into chi square versus distance from the nucleus, that is r. It is 0 at the nucleus but increases gradually, reaching maximum at r is equal to r naught. For 1s orbital, it is 52.9 picometer, which is nothing but the Bohr's radius for hydrogen atom. Beyond r0, the curve shows a gradual decrease at the longer distance from the nucleus. The radial probability distribution curves for 2s, 3s and 4s orbitals are shown below. In 1s orbital, we have one peak. In 2s orbital, we have two peaks. In a 3s orbital, we have three peaks. So in case of the 2s orbital, in between the two peaks, the point touches to the x-axis and that point is known as a node. Therefore, 1s orbital is not having any node because it is having only one peak. 2s is having the two peaks and it is having one node. 3s is having three peaks and it is having two nodes, and so on. In general, the s orbital is having n-1 nodes. When I plot the graph of 4 pi r square into dr into chi square versus the distance from the nucleus to the 2p orbital. The 2p orbital contains only one peak. So, as shown in the figure, the 3p orbital is having the two peaks and one node. Similarly, the 3d orbital is having only one peak because the s starts from 1, p starts from 2, 3 starts from, d starts from 3. Suppose if I say how many nodes you come across in 6d orbitals. So when I say 6d orbital, how many nodes? The d starts from 3, 3 is having 0, 4 is having 1, 5 is having 2, 6 is having 3 nodes. Similarly, how many nodes are there for 6p? If they ask, p starts from 2, 2 is having 0, 3 1, 4 2, 5 3, 6 4. So So we come across 4 nodes in 6p orbital. This is how the number of nodes are calculated. So from the above the radial probability distribution curves, we can conclude the following things. Number 1, in each case, the probability of finding the electron at the origin is 0. At the origin is nothing but it is the nucleus. That shows that in the nucleus you don't come across any electron. The distance for the maximum probability of finding an electron in an orbital increases with the value of its principal quantum number. For example, the distance for 1s, 2s and 3s orbital is in the order of 1s is less than 2s, which is less than 3s, as is the evident from the curves of these orbitals. The total number of peaks appearing in the curves for s, p and d orbital is equal to n, n minus 1 and n minus 2 respectively, where n is the principal quantum number. For example, the number of peaks for 1s, 2s, 3s, 2p and 3p and 3d orbitals are given as for 1s it is 1 peak, 2s it is 2 peak, 3s it is 3 peaks. The p starts from 2, therefore 2p is having only 1 peak, 3p is having 2 peaks and d starts from 3, so 3d is having 1 peak respectively. Suppose if I say 5d is having how many peaks? So 5d is having 3, the d starts from 3. So 3, 1, 4, 2, 5, 3. So 5d is having 3 peaks, whereas 5s is having 5 peaks. From the curve of 1s orbital, the value of r at the peak is 52.9 picometer, which is equal to Bohr's radius. For 2s orbital, the probability of finding an electron is 0 at r is equal to 0 and at r is equal to 105.8 picometer also. The second peak is maximum at r is equal to 264.5 picometer. Therefore, the radius of the second orbit is 264.5 picometer and the region, the distance from the nucleus, the node region from the distance from the nucleus is 105.8 picometer. In a 2s orbital, at the distance r is equal to 105.8 picometer, the probability of finding the electron is almost 0. This is called a node or nodal plane or nodal surface. All means the same. For any orbital having principal quantum number n, there are always n minus 1 nodes. 2s and 2p orbitals have slightly different energies and both of them have greater energy than 1s orbital. 2s orbital is bound more tightly to the nucleus than 2p orbital. Therefore, 2s orbital is having slightly lesser energy than 2p orbital. Now coming to the angular wave functions. Dependence of angular wave function on quantum numbers and sign of angular wave functions. The angular part of the wave function depends on azimuthal quantum number and magnetic quantum number values and is often referred to as atomic orbitals. These gives the shapes of atomic orbitals that depend on the angle theta and phi. The expression of s orbital is independent of angles theta and phi, and hence s orbital is spherically symmetrical. The angular part of the wave function psi may be positive or negative depending on theta and phi values. The s orbital is positive all through, although because it is independent of theta and phi, and there is no change in its shape, which remains spherical. Therefore, the shape of the s orbital is spherical and it is having the positive. The expression of p orbital is dependent on angles theta and phi. Hence, it is having dumbbell shape structure. The p orbital has one lobe positive and the other lobe negative, because the angular part of the say pz depends on cos theta, which has positive sign between theta minus 90 degree and 270, 0 minus 90 degree, theta minus 90 degree and 270 minus 360 degree, and negative sign between 90 to 180 degree and 180 to 270 degree along z-axis. I repeat, the cos theta, which has positive sign between theta to 90 degree and 270 to 360 degree, and negative sign between 90 to 180 degree and 180 to 270 degree along the z-axis. The p orbitals have spherical lobes, whereas the chi-square plots give elongated lobes. The shapes and sign of px and py orbitals are similar to pz orbital. One lobe is having positive sign, another lobe is having negative sign. In case of s orbital, it is having only, it is spherical, it is having only positive sign. The shapes of d orbitals are double dumbbell in a shape. Each dumbbell is having positive and negative sign. There are 5d orbitals. Among the 5, 3d orbitals are in between the axis and 2d orbitals are on the axis. So dxy, dyz and dxz orbitals are in between the axis. Here each lobe is positive environment and the another lobe is negative environment. The dx square minus y square and dz square orbitals lie along the axis, and their signs are also shown in the diagram. The shapes of f orbitals are triple dumbbell in shape, which are complicated in structure. Now this is a slide I am showing, the first one, a probability of finding the electron or the orbital. So the orbital is a region around the nucleus where there is a probability of finding the electron. So for 1s orbital, when we plot the graph of chi square versus r, or the radial wave function, that is r is to r versus r, we get a graph. That graph shows there is no node. The same for 1s orbital, when we plot the graph of 4 pi r square into chi square, it is a three-dimensional figure. That is, the orbitals are three-dimensional figures. That's why we are taking the volume of the orbitals. That's why we are multiplying by 4 pi r square into dr. So we get only one peak for 1s orbital. Now when I take the 2s orbital, we get the 2 peaks. 3s orbital, we get the 3 peaks. Similarly, for 2p orbital, we have only one peak. For 3p orbital, we have two peaks. The d starts from 3, therefore 3d is having only one peak. The same even below the diagrams are shown. So this is the distribution curves. What I have explained, the same things are there even in the graphs. The angular nodes. So node is a region around the nucleus where there is a probability of finding the electron least. Therefore, here the psi value becomes 0. So, and the other graphs are also, which I have already explained, the same things are there even here. So these are also the graphs. So in the initially I have shown the 1s, 2s, what you can say the graphs and the nodes also, which I have already explained. The same things are there here also. In this also have shown, so what is the shape of the 1s orbital, 2s orbital and 3s orbital. 1s orbital we don't have only, there is no node, but 2s is having only one node which is represented by a white, and the 3s orbital is having two nodes which are also shown by a white space. And also their corresponding the diagrams, radial probability density diagrams or radial probability distribution curves. Now we have already discussed about the nodal properties like angular nodes and radial nodes. The s orbital have no angular nodes, therefore it is spherically symmetrical. P orbital has one angular node, therefore the psi is equal to 0 we have there, and the 2p is having no nodes, 3p is having one angular node, and so on. The number of angular nodes for s is 0, p is 1, d is 2. Coming to the radial nodes. For s orbital have a maximum in psi at the nucleus r is equal to 0. For other orbitals like p, d and f, the psi is equal to 0 at nucleus due to angular nodes. All orbitals decay exponentially at large r values. The nodal surface where psi is equal to 0 with psi changing its sign either side of the node. The number of radial nodes is given by the equation n minus L minus 1, which already I have explained in my earlier. The total number of nodes how we can calculate is also shown here. So this is a diagram shows the nodal planes. So the p orbitals are dumbbell in a shape, and these dumbbell shape orbitals, so the in between the two we have a nodal plane or a node region where there is a probability of finding the electron is less. In this, yellow color shows a positive part of the lobe and green color shows the negative part of the lobe. So this is another diagram explaining the same thing. It is for the top three are for the p orbitals and below they are for the d orbitals. P orbital is having one nodal plane, whereas the d orbital is having two nodal planes or the two nodes. So these are the things which you have to remember regarding the radial distribution curves. Thank you.